Okay, let's finish off chapter 3. So we were discussing Abu al-Wafa's book on geometry for craftsmen. And so I want to look at the final, this construction of a pentagon. Okay, so let's think for a moment how we could possibly get a pentagon. And so we've had a little bit of experience in trying to construct polygons. And so we know that we need either to construct an angle, for example, the interior angle of the polygon, which for the pentagon would be 72 degrees, or a length, the length of the side of the polygon that we want. And for an answer, we can look to Euclid, and Euclid book 13, proposition 9, gives that if you take a segment and you cut the segment such that, so let's say we've got a segment AC, we cut it B, so that AB is greater than AC, and AB is to BC as AC is to AB, and if you think of that, that means the large is to the small as is the whole to the large. And so that's two ratios being equal, so we cross multiply, we see AB squared equals AC times BC. Remember, AB squared means that an area of side AB, and AC times BC, we mean the area of a rectangle of sides AC and BC. And when we cut a segment like that, we have what they call the section and what we call the golden section. And Euclid says that whenever we've got a golden section, then we can construct a circle where AB is going to be the side of the hexagon that can be inscribed in that circle, and BC is the side of the decagon, which can be inscribed in the circle. And if you think about it for a moment, this solves our problem for us, right? Because AB is the side of the hexagon, well, the side of a hexagon is the same as the radius of the circle, right? Because you can cut up a hexagon into 6 equilateral triangles. And so each side of the equilateral triangle is AB, and one of those things is the radius of that circle. So that's good. And BC, the side of the decagon, well, that gives us a pentagon because a decagon is a circle cut up into 10 pieces. We just stick 2 of them together and we cut into 5 pieces, and that gives our pentagon. Okay, so here's the problem. Construct a regular pentagon in a given circle with radius equal to the compass opening. So remember, we've got the rusty compass. So really we can only transfer one length from one place to another. Okay, so given a circle that has the radius that we want, we find its center. That was a homework problem. And then we just draw in any diameter. Okay, so at one end of the diameter, we erect a perpendicular, and we let that perpendicular be the length, the radius of the circle. So remember, AD, we can put AD is the radius of the circle, and with our rusty compass, we can put that anywhere we want. So AE equals AD. Okay, so then we bisect AD at Z, and then on ZE, we mark off H such that ZH equals AD. So again, we use our rusty compass for that. We can then bisect ZH again. We can bisect that at T. And then we construct a perpendicular of EZ at T. Okay, and we draw that line and we extend it till it hits I, which is where it intersects with the diameter extended out that way. Okay, and so then we get our point I, we get our rusty compass, and we mark off L and M. That's saying IM and IL is equal to AD. And the claim then is that ML is one side of the desired pentagon, and we can then just take that around we can then, what we can then do is, if we take the perpendicular bisector of MO, right? So remember, we've got O, so we bisect MO, and we put that bisector up. That's going to hit it at N, so that's going to bisect the circle between M and O, and we do the same thing, bisect between L and O. That's going to give us P. M, N, O, P, L are going to be our points of our vertices of our desired pentagon. Okay, why does this work? So we go back to our construction, and what we see is that we have very cleverly constructed some congruent triangles. So TIZ and AEZ are congruent triangles because we've got sides equal and they share the angle. Well, first off, you should be able to see that the angles are equal because we've got right angle, both are right angle triangles, and they share an angle, and they have one side in common. So that means they're congruent right angles. So that means we can use Pythagoras' theorems. And so we get ZI squared can be written as DA squared plus AZ squared. And so we solve for DA squared. So DA squared equals ZI squared minus AZ squared. We've got a difference of two squares, so we can write that as ZI plus AZ times ZA minus AZ. And when we look at what that means, we see that DA squared equals ID times IA. And there's our golden section right there. So we've taken that line IZ and we've cut it into the golden section. So that means AD is our hexagon length, and it is because it's the radius of the circle. So great. So the decagon that we get is the decagon for the circle we started with, and IA is the side of the decagon. And then we see that we have that we can then see that AI is actually equal to AL because we've got a bunch of similar triangles that we can then just do the geometry there to prove that. Okay, so AL is the side of a decagon. So that means AL, that arc AL is 1/10 of a circle. Well, if we just flip it up, we get AM is also a 1/10 of a circle. So that means LM is 1/5 of a circle. And so that's why we've got our pentagon. And in fact, this construction gives us a decagon, right? Because we could use that side AL, and by doing stuff, we can make a decagon. But the important thing is we've got our pentagon as we wanted. It's a little bit complicated, but actually it's pretty nice. I've actually seen videos of was an old video of craftsmen in Iran, and they were actually making pentagon tiles and using a process like this where they'd cut things off and then, in like a few minutes they'd make a perfect pentagon. That's pretty cool. And then just as a final comment, besides giving exact constructions, Al-Wafa also talked about doing approximations. So for example, a heptagon, which we know we can't have an exact compass and ruler construction of, you can do a pretty good approximation by using half the side of an equilateral triangle. Okay, I think I'll set that as homework for you to figure that out. Okay, that finishes off chapter 3.